Okay, welcome back, class. Today's lesson is on centripetal force. But before we go on to centripetal force, let's review what you should have already studied about uniform circular motion. This is the second uniform circular motion lesson. So when we started uniform circular motion, we looked at when something goes around in a circle, we have to know the distance it goes. That's the circumference of the circle, which is 2 pi r, and the unit for that is meters. Then there's the period, the amount of time it takes to go around the circle. We call that t, and that is a unit of seconds. We have the frequency, which is it's a little bit like period. It's rotations per second. It's a different way of measuring, where t measures what many seconds it takes to go around once. Frequency measures how many times it goes around each second. So they're actually inverses of each other, where the unit of period is seconds, the unit of frequency is 1 over seconds, or second to the negative 1, seconds inverse. And frequency is equal to 1 over the period, or period is equal to 1 over the frequency. So you can go back and forth between the two. Then we talk about the velocity, v. Well, that's the distance traveled divided by the time. So the distance around the circle we know is the circumference of 2 pi r, and the time is the period, t. So the velocity is 2 pi r over t. But since f is 1 over t, we can also say it's 2 pi r times f. Finally, you learned, let me just open this thing up. You learned about centripetal acceleration. And you learned that was it turns out to be equal to the velocity squared divided by the radius, v squared over r. So that's our centripetal acceleration. Let me turn off this little thing here, if I can. There we go. So the question for today is really, okay, if this thing is, so we're saying if something goes in a circle, it's actually always being accelerated towards the center of the circle. In other words, its velocity vector keeps getting pointed towards the circle, curves towards the center of the circle, and that's a change in velocity, so it's actually an acceleration. But you can't accelerate anything unless you have a force. That's basically Newton's second law, right? Newton's second law, and I'm going to try actually using a regular pencil. I was watching Khan Academy the other day, and they don't actually use handwriting recognition, and maybe it goes smoother. Let me just give it a try. I'm going to use the finest line in black. That looks good. So let's, oops, I lost it. There we go. So let's go ahead and say Newton's, oh my God, how did that happen? Try that one instead. Newton's second law says F equals ma. Well, we know that centripetal acceleration is v squared over r, so that must mean that centripetal force is just going to be ma, so m v squared over r. That's the force that pulls something in a circle. For instance, if you swing something around on a string or a rope and it's going around in circles, the tension in that rope is the force that's holding it in that circle, and that force is mv squared over r. So this is our sort of golden rule for today's lesson. F sub c equals mv squared over r. Oftentimes, people talk about something called centrifugal force, and they say that's the force, for instance, if you're riding in a car and it makes a left turn, you feel like you're forced to the right side of the car, and you say that's centrifugal force. Well, physicists say there's no such thing as centrifugal force, because you are actually not being forced to the right when the car turns left. What's happening is that you're being forced to the left by the car, and you're accelerating to the left, and it says centripetal force to the left, the force of the car on you, pulling you to the left. It's not you being pulled to the right. You make the mistake of thinking that the inside of the car is stationary, but the inside of the car is moving to the left, and it's forcing you to the left when you make a left turn. So let's see. Let's go to page 140, example 5. So let's see, page 140, example 5. We have a model airplane, has a mass of 0.90 kilograms, okay? Mass equals 0.90 kilograms. Okay, moves with a constant speed on a circle that is parallel to the ground. The path of the airplane and its guideline lie in the same horizontal plane. Because the weight of the plane is balanced by the lift generated by its wings, find the tension T in the guideline. Length 17 meters. So that's the radius, 17 meters. Looks like we have two significant digits. For two different speeds, so we've got V equals 19 meters per second, and V equals 38 meters per second. So let's try a free body diagram here. Okay, that dot represents the airplane. So downward we have mg. Upward we have, we'll call it L for lift. To the left, say, we have T, the tension in the string. So you might say to yourself, well, how come there's nothing to the right to balance that out? Because the airplane is accelerating inward towards the center of the circle. So we would expect that the sum of the forces is going to equal the mass times the acceleration. So in this case, T, which is the only force in the horizontal plane, has to equal mv squared over r. So this is quite simple. In the one case we have T equals 0.90, that's m, times v, 19, that's v, squared over 17, which is r. In the other case, we have T equals 0.90 times 38 squared over the same r of 17. So we can calculate those two tensions. Let's see. I've got 0.9 times 19 squared divided by 17. That's equal to 19 newtons. And then we have 0.9 times 38 squared divided by 17, and that's equal to 76 newtons. And that's all there is to it. Alright, so let's get a new page and give you a problem to try. Alright, so first of all, I'll put the centripetal force equation up here. F sub c equals mv squared over r. Now I'm going to make this a little trickier, so you'll have to remember other things, like that v equals 2 pi r over t, and it's also equal to 2 pi f. Okay, because here's the problem. I wrote down a problem for you to do, and here it is. Maybe what I'm going to do is I'm going to pause and I'm going to type it. Okay, so I'm back. Here's my problem for you. A person has a mass of 100 kilograms and is on a ride that spins with a period of 40 seconds and a radius of 10 meters. What is the force exerted on the person by the seat of the ride due to the spinning motion? Okay, so why don't you go ahead, I'm going to pause and you solve this, and then I'll try to solve it, and we'll see if we get the same answer. Okay, so a first step is usually a good idea to write down your givens. Okay, so let's see, we've got M equals 100 kilograms. We've got T equals 40 seconds. We've got R equals 10 meters. Okay, so let's see. Well, we know that FC equals mv squared over r, but we need v first. V is 2 pi r over t. So let's find v. V equals 2 pi r over t. That's going to be 2 times pi times 10 divided by 40. All right, let me get out my calculator. 2 times pi times 10 divided by 40. That's going to be approximately, let's see if I did that right. 2 times pi times 10 divided by 40. That is 1.57. Okay, let's do that then. Wait a minute. Okay. Yep, 1.57. 1.57 meters per second. Okay, 2 pi times 10 divided by 40. All right, so now we can use our FC is mv squared over r. So the tension, or what, we don't have a tension in here, hold on a second. The force causing this person to rotate, the seat on the person, is going to be mv squared over r. mv squared over r. Okay, m is 100. V is 1.57 squared over r, which is 10. Let me give that a try. I already have the 1.570796327 on my calculator, so I'm just going to push the squared button. Okay. Now, I'm just going to multiply by 10 because I know 100 over 10 is 10. Okay, that looks like 24.7, I'll call it. 24.7 newtons. So what's that like? Is that a lot? Well, if this person weighs 100 kilograms, how many newtons do they weigh? Remember, force is mg, right, where g is gravity, right? So 100 times 10. So this person weighs 1,000 kilograms. So this ride is not that big a deal, right? It's going pretty slowly. All right, I'm going to just pause and double check my map here. Yeah, that looks good. I think I made a mistake when I first wrote this, and I thought it was going to be a lot, but it's not really much. So there's our answer, 24.7 newtons. That's the force exerted by the person in the ride by the seat due to the spinning motion of the ride. So really, there's not a whole lot going on here. Let me go back to the first page, and there it is. That's the key to this whole section. F sub c, the force, centripetal force, is mv squared over r. The main thing you have to understand is that's the force that pulls the object towards the center of the circle, and that's what causes it to curve in towards the center as opposed to going straight. A lot of people think if you swing a weight around on a string and you cut the string, the weight will fly straight out, but it won't. It will fly tangentially to the curve, because all of a sudden there's no more force pulling it towards the center, and so it's just going to be pulled, it's just going to move along according to Newton's first law in a straight line in whatever velocity vector it happens to have at that time. That's all I've got for you today. Tomorrow you should bring in your notes from this, including the worked out problem, to get full advanced credit on your homework, and I'll give you some problems to work on.